The last transform of interest in this course is the Z transform. To understand why the Z transform is interesting or necessary for us, let's go back to the formula for the DTFT, where the Fourier transform, denoted with the curly f, or x of omega, is given by this formula. Similar to the Fourier transform of continuous time signals, the DTFT x of omega for discrete time signals doesn't always exist for all signals or is unbounded for some frequencies. So we generalize the formula for the Fourier transform by multiplying the signal x of k with a complex exponential e to the power of minus sigma k, which gives the new signal x dash of k. As long as x of k doesn't grow faster than exponentially, we can choose sigma sufficiently large so that x dash of omega, the DTFT of x dash of k, exists, so that we get the Fourier transform of a slightly different or manipulated signal. Another option to understand this generalization is to combine the two complex exponentials in the sum so that we get the sum from minus infinity to infinity of x of k times e to the power of minus sigma plus j omega k. As a last step, we denote the complex exponential e to the power of sigma plus j omega as the new complex variable z, which yields the Z transform of the discrete time signal x of k, denoted as x of z. Since we usually deal with causal signals and systems, we only take the sum for k equals 0 to infinity, which yields the unilateral Z transform. And again, in contrast to the Fourier transform, we can here choose sigma sufficiently large to ensure that the Z transform x of z exists. And all values of z for which x of z exists are collected in the region of convergence, often abbreviated as ROC. And if the region of convergence doesn't exist, then the Z transform x of z doesn't exist either. For causal signals, the region of convergence lies outside a circle around the origin, and the radius of this circle depends on sigma. So if sigma has to be chosen relatively large, the region of convergence is lying outside a relatively large circle. The inverse Z transform gives an expression for x of k, but it's cumbersome to calculate because it involves solving the integral around a closed, counterclockwise contour within the region of convergence. As a first example, let's calculate the Z transform of the discrete time exponential function a to the power of k times the unit step function. We'll start with the formula for the unilateral Z transform, which is suitable since x of k is a causal signal due to the multiplication with the unit step function u of k, so that x of z is equal to the sum, for k equals 0 to infinity, of a divided by z to the power of k. To solve this, we need to use the formula for the geometric progression. And since we have an infinite sum this time, we have to express this sum as a limit of a finite sum. Then the Z transform x of z is equal to the limit for n going to infinity of 1 minus a divided by z to the power of n divided by 1 minus a over z. If the magnitude of a divided by z is strictly less than 1, then a divided by z to the power of n will converge to 0, such that x of z is equal to 1 divided by 1 minus a over z. But for other values of z, for which a divided by z has a magnitude greater than 1, x of z will approach infinity and will hence be undefined. So x of z is equal to 1 divided by 1 minus a times z inverse and has the region of convergence magnitude of z is greater than magnitude of a, which are all values of z outside a circle which has as a radiance the magnitude of a. As a second example, we will derive the Z transform of a causal cosine multiplied with an exponential function. As a first step, we will use Euler's formula to substitute the cosine term. Then x of k can be written as a sum of two causal exponential functions, so that the Z transform consists of the Z transforms of the individual exponential functions, for which we have already derived the transform in the previous example, so that the Z transform simply consists of two terms corresponding to the Z transforms of the two exponential functions. Combining the two terms and using Euler's formula yields the final expression for x of z, for which the region of convergence is the combination of the region of convergence of the individual terms, which yields that z by magnitude has to be greater than the magnitude of a times e to the power of plus j omega 0 or minus j omega 0, which in both cases yields that the magnitude of z has to be greater than the magnitude of a.